Hello, this is Brandon Mills with the Diabetes Prediction Using Machine Learning project from the Indigenous Youth Data Analytics and AI course. So first, I selected a database that I believe reflects the one we were supposed to use since we weren't provided a database. It's from UCI Machine Learning, and it's the Pima Indians Diabetes database. So I imported all the modules I believed I'd need and loaded up the database, and you can see right away that for the classification problem, it already has an integer binary representing true and false for diabetes. And the remainder of the 8 variables are to be our inputs for classification. The data from Kaggle already cleaned with no nulls and no duplicates, so I just sent it straight to X and Y variables, as well as fitting the scalar to the data. I retained 20% and set a random number for the random state, and verified that it kept 20% for the test after the training. And then I just have a block here where I decided what neuron layers I was going to use. I start with a depth of 16, which is just double the number of input variables, then 8. And then since this is a classification problem, we have the sigmoid neuron at the end to decide true or false. So here I just imported the Atom optimizer since I had to input custom learning rates, as well as re-importing the dense and sequential since I was having some weird issues with that. So I defined the learning rates, epochs, and batch sizes that were recommended in the slides, and then I wrote a looping script that creates a model for each learning rate, epoch, and batch size permutation, and stores the statistics on performance into a data frame. So you can see that it compiles using Atom and the custom learning rate. History is created, and I append to results the data that I would like to store. So in this data frame, you can see the final training loss, accuracy, value loss, value accuracy, the standard deviation, and the overall test accuracy, recall, precision, F1, and their confusion matrices. After that, I moved to the visualization step. So I generated 2 data frames and 2 graphs. The first data frame shows the average test accuracy with the highest accuracy bolded. So the best accuracy was seen 64 batch sizes, a learning rate of 0.001, and 50 epochs with a 78% accuracy. But the best for the loss of standard deviation, which would be the minimum, was learning rate of 0.1, batch size 16. Batch size 16 and 150 epochs. And then I have these 2 graphs just for visual comparison, where you can see the highest accuracy reflected here under the 0.001 batch size 64 color there. And that's at the 50 mark. And for the loss of standard deviation, you can see that if you wanted to maximize stability, that one is actually by far the best option for our data. After that, I moved on to analyzing what the professor asked us to, which was the accuracy, precision, recall, the F1 score, and the confusion matrix. So I used the highest accuracy overall to determine a kind of best. For a medical problem, you might want to optimize for recall, since that minimizes the amount of false negatives to maximize the number of cases that could be medically significant that are caught. But I have our bar chart here showing the 79% accuracy, 72% precision, which is the confidence behind a positive outcome. But the actual recall rate, or the accuracy of positives, is 65%. The F1 score of 70 is good, but not great for a medical scenario. That's my analysis of the Pima Indian database. And I have the hyperparameter analysis here as well, which you can pause and read if you would like. Yeah. Thank you very much.